Thanks. Thank you for inviting me to give a talk here. And thank you everyone who is here, though I don't see you, but mentally I'm with you in Nottingham. So let me first describe the object that I've been studying. So I call it the Morse discriminant. And the data that we start with is a set, a finite set in one-dimensional lattice, such that the length of the convex hull is at least 3. This is just to make the situation not very trivial. And for now, let's just ask so that the set affinely generates the lattice Z. So pairwise differences of elements in the set A generate the lattice. And then so I can consider the space C, the space that I will denote C to the power A. And this is going to be the space of all around polynomials with support A. Here is a little example that will be with us throughout the talk. A is 1, 2, 3, 4. And then C to the power A are just polynomials with complex coefficients and degrees 1, 2, 3, 4. So in this space CA, we are interested in the following 2 strata, generally speaking, of codimension 1, which are the Caustic and the Maxwell stratum. So the Caustic would contain all polynomials that have a degenerate critical point. And on the real picture, you can see that, well, just in the neighborhood of this point, the function looks like x cubed or even more than that. And the Maxwell stratum would contain polynomials that have a pair of coinciding critical values taken at distinct points, just like here. So immediately you would see maybe why I'm interested in the set A that doesn't contain 0. I put that that condition. Well, actually, it's not going to change anything, because if you add a constant monomial, then the graph on this picture will just be shifted, but it won't affect the polynomial being belonging to Caustic or Maxwell stratum, or not belonging to any of those 2. So these constant terms, they don't matter, and that's why it's comfortable to just consider sets without constant terms. So without 0. Yes?
Sorry if I chip in. Can I quickly ask a question? So what do you mean with coinciding critical values? Like the same type of critical value?
No. The critical value. So at 2 critical points, critical values, so the values of the polynomial at these points.
Okay.
Yes, they coincide. And this is this corresponds to this picture. So a polynomial is Morse if it doesn't belong to either of these 2 strata. And as I said, these strata, generally speaking, are of codimension 1, so given by polynomials, they're hypersurfaces. And at least in the case 1, 2, 3, 4, the easiest non-trivial case, one can explicitly, nicely compute the polynomials defining the Caustic and the Maxwell stratum. So for the Caustic, you might recognize the coefficients. They look similar to the coefficients of the discriminant of a cubic equation. And this is not a coincidence, because I said that the Caustic would contain polynomials that have a degenerate critical point, but that means that the first and the second derivatives should vanish. So basically, the Caustic would would be the same thing as the discriminant. And HM, is everything okay?
Yes, just a few guests are joining.
Okay, sorry. Just so, and the Maxwell stratum, which the polynomial which I denote, so the polynomial defining the Maxwell stratum, which I denote by HM. Well, in this case, it's somewhat nicely looking polynomial, but in general, the bigger the support set A is, the harder and the more nasty this polynomial becomes. So if we want to compute it explicitly, then of course that's not going to be very promising. So basically the main idea of my project was to try to describe the Newton polytope of primarily the Maxwell stratum, because for the Caustic it's already known. It's since it's discriminant, so it's known from the results of Gelfand, Kapranov, Zelevinsky. So the idea was to try to do something about the Maxwell stratum. So in the end, what turned out to be more comfortable in some way was to try to do the following problem, to describe in terms of the set A, so kind of combinatorially somewhat, the Newton polytope of the Morse discriminant, namely of the polynomial Maxwell stratum squared times Caustic. So there are different combinatorial reasons why I'm still interested in the product, why I still want to multiply stuff by the Caustic. Also, the fact that I take Maxwell stratum squared is purely of convenience, so that like when I compute the support functions, I don't have to divide by 2 just to make formulas look better. But if you are just interested in the polynomial defining the Maxwell stratum, purely this one, then all of the methods that I will describe can be tailored to this. And I will later in the talk, I will show you the exact moment when you can change what you are computing so that it fits your needs. But for now, let's agree with this definition. And for example, for the set A that we have seen before, 1, 2, 3, 4, if we just multiply those two polynomials and open the brackets, the corresponding Newton polytope would be a pentagon in R4 with this nice coordinates. And later in the talk, not even once, we will come back to this polytope too, so that because we'll have different views on how to see its vertices, like what they correspond to. So of course, instead of trying to find the polytope, or I don't know, so this problem seems sort of clear, I think, in the statement, but probably not even clear how to approach, how to even try to do it. So first step is to realize that instead of the polytope itself, we can compute its support function. And I will quickly remind what it is, just a fixed notation, because there are, of course, different conventions. So what I call the support function is as follows. So suppose you have a polytope in Rn, and I define its support function as follows. I take as input a covector from the dual space to the one that contains the polytope, and as output, I give the maximum that this covector, if viewed as a linear function on restricted on my polytope, attains in my polytope. So here is a little example. If the polytope is a triangle in the plane drawn here, then on the right we can see what the behavior of the support function is, right? So basically this function is piecewise linear. And what we can see is that the linearity domains of this function are in bijection with the vertices of the polytope. So let's just see a bit this example. So for example, if your covector has non-negative coordinates and the first coordinate is bigger than the second coordinate, so your covector ended up in this cone, then it will attain its maximal value at the vertex 1, 0. And to actually see what value is going to be, you have to just pair the coordinates of your vertex with your covector. So that is why in this cone, the support function is just linear, and the coefficients are the coordinates of the corresponding vertex. And the same holds for all other linearity domains. So we have such a bijection. And therefore, knowing the vertices of the Newton polytope or polytope that we want to compute, knowing the coordinates of these vertices is the same as actually knowing the linearity domains of the support function and the coefficients that this support function has in each of those linearity domains. So these are two equivalent things, and we will concentrate on trying to compute the thing on the right, the support function. So one more remark here is that if you take some random covector, then most likely it will end up in one of those full dimensional linearity domains in these cones, and you have to really try much harder to find a covector that will end up on say attain its maximal value on the edge or on the polytope itself, right, and so on. So one more thing that I have to say, that if the dimension of the ambient space is strictly bigger than the dimension of the polytope, which actually is true for the Morse discriminant and even usual discriminant, classical discriminant, then all I said is true, except for this full, so linearity domains, this full dimensional cones will also contain common subspace of complementary dimension to the polytope. Are there any questions? Because I hear that some microphone is not muted and.
No, I think there's someone who just joined. Okay.
So now I will formulate the answer, or at least the format of the answer that I obtained. And this will kind of conclude the first part of the talk. And then the second part of the talk, I will explain the approach, how I did it, and in general, how one could tackle same flavored problems as well. For the formulating the answer, it turned out that the most comfortable language would be the tropical language. And since again, in terms of tropical geometry, there are also a lot of different conventions. I have to recall the basic definitions that we will need, but it's going to be real quick. So we work over the tropical semi-ring, which is just real numbers together with minus infinity added, and two tropical operations, addition and multiplication, where multiplication is just the usual addition, and addition is, I define it as a multi-valued operation that with a pair of numbers, if they're different, associates their maximum, and if they are the same number, then it gives an entire interval from minus infinity to this number. So a tropical Laurent polynomial with the support A, right? So we are still living in a world where we have a support set, and all the monomials of your polynomial should be contained in that set. So it's just a tropical sum of tropical monomials. Nothing can be more straightforward than that. And if you open up the brackets and use a slight abuse of notation, forgetting for a while about this function being multivalued, then it's going to be just a maximum of some affine linear functions, some list of affine linear functions with slopes in the set A. We will also need the definition of a tropical root. So tropical root of a tropical polynomial is a point where at least two monomials of the tropical polynomial attain this maximal value, which I also will refer to as a critical value. And if suddenly it all sounds very not clear, just give me a minute. You'll see pictures in a couple slides, and it will all become very clear. So before I pass to pictures, I still need to kind of get not get too far from the situation we are in, from the problem we are solving. So as I said, we are computing some support function of a polytope. So this support function takes as input a covector. And in our case, the covector will lie in the space dual to r to the power cardinality of a. So like all the coordinates will be indexed by the set a. Therefore, actually the covector we can view as a function from the support set to r. And then with the covector, we can associate a tropical polynomial whose tropical coefficients are going to be just the coordinates of this covector. And if that wasn't clear, here's an example. Suppose we have a set -3, -1, 1 to 4. Then its cardinality is 5. So a covector would have 5 coordinates. And with the covector 3, 5, 2, 5, 1, for example, we would associate a tropical polynomial, which in this form would be written as -3x plus 3, then -x plus 5, x plus 2, 2x plus 5, 4x plus 1. So the max of these functions. So again, as input, we took a covector. And for now, as output, we obtained some tropical polynomial. And we will work with this tropical polynomial. So, but before we work with it, let me draw something. So suppose we have some tropical polynomial and we want to draw a graph of it. How would we proceed? It's a max of some list of affine linear functions. So we can draw them one by one. So we do it. And once we're done, we take the max. And then we see that there are points where the slopes change. Those are exactly the points where our function is actually not defined. I mean, it's multi-valued, right? So we have to put those vertical intervals to -infinity. So these 3 points are actually the roots of the tropical polynomial, because at least 2 monomials of the polynomial attain the maximal value. And these heights, so these values, I call critical values, as I said. These 2 gray lines are a reminder that actually out of those tropical monomials, not all are going to make it to the top. So not all are going to take part in this, forming the top part of the tropical curve. And in the classical sense, I mean, if you are familiar with, say, the results of Gelfand, Kapranov, Zelevinsky, and the classical discriminant story, there only the shape of the tropical polynomial would matter, but the monomials that never get to the top, they are, even I saw in the literature, they're called insignificant or something like that. So they don't matter in the classical case. But in the problem I was solving, surprisingly, it turned out that those monomials also matter. And we also have to take care of them as well. And that's somewhat surprising, because it kind of gives a new way to look at tropical polynomials and like actually consider them as polynomials, not as just those functions, like piecewise affine linear functions. So so here is a tropical analog of the notion of a non-Morse polynomial that I have come up with using some completely different approach that I will explain later today. So we will now get acquainted with non-Morse tropical polynomials. So a tropical polynomial can be non-Morse due to the following 2 reasons. So one of them is if it gets to the so-called tropical Maxwell stratum, and that is if at 2 different roots, the corresponding critical values coincide, just like drawn here. And it's really, I called it tropical Maxwell stratum because it really reminds of the classical picture, this configuration. There is one more reason why a polynomial can be non-Morse. And this is when it gets to the so-called tropical caustic. And this one is a bit more tricky to explain, but I think we'll manage. So as you remember, when we drew the graph of the tropical polynomial, we drew some auxiliary lines, which are the graphs of the affine linear functions that are in the tropical polynomial. And let's suppose we completed the drawing the way I explained, but didn't erase those auxiliary lines. So this will help us. The idea is as follows, that at every root, at least two monomials attain the maximal value, or we can say at least two monomials attain the same value at this root, maximal or not, right? So at this root, these two monomials attain the same value. At this root, these two monomials attain the same value, and so on. But what if at some root, more than one pair of monomials attains the same value, like here? So at this root, there is this pair of monomials that intersected at the same point this vertical interval to minus infinity, and also this pair of monomials which actually attain this maximal value. So if this is true, if there are at the root at least two pairs of monomials that attain the same value, then I say that the polynomial is not Morse because it got to the tropical caustic. And this is a classical situation. Of course, there can be different combinations. So here, for example, these two monomials were insignificant, but actually it can be a combination of two significant ones at some different root or something like that. So now we can go to the format of the answer to the main question about the tropical, so about the Newton polytope of the Morse discriminant, I'm sorry. So again, we wanted to describe the polytope, the Newton polytope of the Morse discriminant. So it's MA. So it is the same thing as to compute its support function, which I would denote mu A. So also we discussed that a generic covector would attain its maximal value on a vertex of our polytope. Or in other words, it would belong to some full dimensional cone, which is the linearity domain of the support function. And in order to actually describe the polytope, all we want to know for every linearity domain, so for every covector, to which linearity domain it gets, and what are the coefficients of the support function there. So this is all clear. And the format of the answer is as follows. So we take a generic covector, and again, those genericity conditions I will explain actually later. They will follow from basically the computations and trying to solve the problem. But if it satisfies those certain genericity conditions that we will discuss later, then the corresponding tropical polynomial that we associate with this covector is going to be Morse. So it's not going to belong to the Maxwell stratum, tropical Maxwell stratum, or tropical caustic. So it will be Morse. And if that's the case, then from this Morse tropical polynomial, I can read data, some certain tuple of data, which I can only extract from the polynomial if it is Morse. We will see later. I will show you what data is. And actually using this data, I can write down a formula. I will not show you any formulas today because they're kind of long and employ a lot of notation. But reading from this data, I can write you down the coordinates of the corresponding vertex of the Newton polytope. So this is the idea. Covector, tropical polynomial, the certain amount of data from tropical polynomial, vertex, kind of this process. So here is what I mean by combinatorial data. I really would say that you shouldn't look at the format of the data, just only at what it is. So I took the support set -3, -1, 1 to 4. We've seen that before. And actually, I didn't write it here, but I also took the same covector that we considered in an example. So anyway, for your convenience, all monomials are written next to the corresponding affine lines, so you can see what the tropical polynomial was, and therefore what the covector was. So this tropical polynomial is Morse, and we can extract data. So first of all, we can write down a list of all slopes that form the top part of the tropical curve. So if you heard this story with classical discriminant and secondary polytopes, that would be the subdivision. I don't know if it says anything to you. And in this case, it's -3, -1, 2, 4. So then I need to remember from bottom to top the order of the critical values attained at the roots, like which is the lowest and which is the highest. And I can record it somehow. So here is this critical value goes before this one and then before this one. So I somehow wrote it down. And this data you can only read if your polynomial does not belong to the Maxwell stratum. Because if it belongs to the Maxwell stratum, then two critical values will be at the same height, and then you won't be able to tell which one goes first and which one goes last. Moreover, if your polynomial doesn't belong to the caustic, then you can get one more piece of information which looks somewhat big, but the idea is as follows. So at every root, you can consider the order in which monomials intersect this vertical interval to -infinity, vertical leg. So we know that there are two monomials that attain the maximal value, where we don't care about them. But since this polynomial doesn't belong to the caustic, to the tropical caustic, that means that all other monomials, all other lines, will intersect this vertical leg one by one. So not simultaneously. And then this order in which they do it, I just record. And again, if it belongs to the tropical caustic, then a pair of monomials might intersect this vertical leg at the same point, and I won't be able to tell which one to write first, and so on. But like if they don't belong to the tropical caustic, then this order is well defined, and I can write it down. And using this data, I can restore the coordinates of the vertex of the Morse polytope. So formally speaking, there is a surjection between the set of all possible combinatorial types of Morse tropical polynomials with the given support set A and the vertices of the polytope of the Morse polytope MA. And yes, I have here to emphasize that it is a surjection. So there might be two different combinatorial types of Morse tropical polynomial with support set A that would give me the same vertex, but if I want to just enumerate all the vertices one by one, then it's not a problem. So here is a little example again, 1, 2, 3, 4. So basically showing that each vertex of this pentagon that we have computed in the very beginning can be viewed as a certain combinatorial picture, as a certain tropical polynomial with extra information about those insignificant monomials, because they also matter. So I'm not going to stop here explaining like these pictures. Is just to give like a general impression that kind of I treat every vertex as some combinatorial picture. And we will see very soon, actually, we are passing to the second part of the talk. We'll see very soon another combinatorial way to look at those vertices, which actually has more to do with algebraic geometry in some sense. So before I pass to the second part of the talk, I need to make a very crucial remark that actually helps us a lot and can be used. So if we have a covector as I said, with this covector, we can associate a tropical polynomial, the way I explained it. Now the question is, what if I decide to add some positive number to each of the coordinates of this covector? And I get a new covector gamma prime, and I can, with the new covector gamma prime, associate a new tropical polynomial. So the graph of it, you can see, compared with the graph of the previous tropical polynomial. So the only difference is that if all those coordinates were just increased by some fixed number, that all those legs, right, they just became higher. So this picture kind of rises, but otherwise it doesn't change. So if this tropical polynomial, say, was Morse, and we had some, is everything okay?
Yeah, someone joined again. Just
okay. So if this tropical polynomial were Morse, then it remains Morse. And if there was a certain tuple of combinatorial data that we could extract, then it doesn't change if just all of this picture rises slightly. So that means that if we were in some linearity domain, then adding some positive numbers to all the coordinates will keep us inside this linearity domain. We'll not get out of it. And that's very nice, because that means that we can indeed consider not all covectors, but only covectors with non-negative coordinates. And this gives us a way to look at the world from a different perspective. Namely, as I said, every covector still we can view as a function from the support set A to R, but now since it has non-negative coordinates, it's actually a function from A to R, so non-negative numbers. And with it, I can associate a polygon, maybe with extra information about other points, but the polygon is constructed very easily. So you take the graph of this covector viewed as a function. So and these black dots are actually the points of this graph, for example. And then at the zero level, you add the support set itself, the set A, and take the convex hull. So I'm pretty sure that, again, if you dealt with the secondary polytope, so the classical discriminant in the univariate case, then probably you saw those pictures, so those roofs, those tents. And this is very nice here. And we will later play with pictures like this. But I have to just say that whatever I said in the tropical language can be translated in the language of this n gammas. For example, if you remember, I was talking about monomials that didn't get to the top of the tropical curve. So here we can see those monomials on this picture as well. Those are the points of the graph of this function that never get to the convex hull, to the boundary of the convex hull. Also, when it comes to classifying non-Morse tropical polynomials, so we can reformulate all these criteria in the language of this unions of trapezoids, of these nice polygons. For example, for a tropical, if the covector was such that the corresponding tropical polynomials had coinciding critical values at two different roots, then the corresponding graph, the corresponding roof, as I explained above, would possess the following property, that continuations of a pair of those non-horizontal edges would intersect the vertical axis at the same point. So these two conditions are actually the same thing. For the caustic, there is also a similar condition, which also probably is slightly more complicated to formulate. But the idea is as follows: so you can consider, so you can connect the points of the graph of this covector on the right by intervals, and then check whether there is an interval that would be parallel to one of the intervals here. So, for example, for the fact that this root has a pair of two monomials that two pairs of monomials that attain the same value, here translates into that there is an interval in this graph that would be parallel to this edge of the polygon and gamma. So, and this might sound very weird, but actually, if you would, if I had to characterize this correspondence in two words, I would just say Legendre transform. But otherwise, just computing everything by hand just like kind of lets you see this correspondence, like really literally computing the roots and comparing the values at the roots attained by some two pairs of monomials and so on. Anyway, so we will play around these pictures, around these polygons. And maybe already you can feel like it's, if we want to relate it to algebraic geometry, if there is some algebraic geometry that comes into play, that means that these polygons might be some Newton polygons of some polynomials or something like that, and we will do all sorts of interesting stuff with it. So if that's what you're expecting, then soon you're gonna get it. So before we pass to explaining the solution to the problem, I want to clarify more the conditions that actually we put on the support set A. So as I said before, it should not contain the zero. It should affine generate the lattice, and it should be at least of length 3. But again, this is to make stuff non-trivial. Actually, I would want an extra condition that a generic polynomial, which belongs to the Morse discriminant in the space of polynomials with this support A, should have either exactly one pair of coinciding critical values or exactly one degenerate critical point of multiplicity 2. So it might sound very strict, but first of all, this is true for already quite a wide range of support sets. For example, at least those that contain all of the points inside their convex hull, or the sets that contain at least 4 consecutive integers. Moreover, there is a conjecture which we haven't been able to prove or disprove, but it's kind of a work in progress in the research group I'm working in, that actually any set that satisfies the first 2 properties, or actually even the first one, would satisfy this third one. So basically, we haven't ever seen a support set that would affinely generate Z, but such that the a generic Morse, non-Morse polynomial would just have something worse than what was described in this condition. So basically, for now, you can just see that whatever I say is true definitely for quite a wide range of sets. And actually, there is a conjecture that says that, well, it's true for all the sets. But it's work in progress. Anyway, now let me show you the key ideas of how to turn this problem into algebraic geometry / singularity theory, combinatorics, and so on. So again, as I said, we start with the generic covector gamma, and which hopefully will end up getting the maximal, so attaining the maximal value at the vertex of the Newton polytope. And as I said before, we can restrict ourselves to covectors with non-negative coordinates. Moreover, we can actually restrict ourselves to the covectors with integer non-negative coordinates. Right? We basically are talking about behavior of a piecewise linear function with integer coefficients inside of its linearity domain. And I want to understand those coefficients. And in order to understand them, I really need to see what happens to covectors with integer coefficients, because then this behavior would describe the behavior of the function for all covectors in this linearity domain. And that is already good news, because that means that these polygons and gamma, these unions of trapezoids that we will talk about, will turn into lattice polygons. So it feels like much more chance that there are going to be some Newton polytopes of something. So, and indeed, we can play with it as follows. We can introduce one more variable t, and consider a corresponding family of polynomials, which I would say, so someone would call it Viro polynomial, someone would call it Hovansky polynomial. But nevertheless, the idea is that, so we are given some covector, and I can consider polynomials in X with support A, such that the coefficients are actually functions depending on this new variable t, which goes to the degree gamma, so the corresponding coordinate of the covector. And the Newton polytope of such a polynomial, if viewed as a polynomial in two variables, is going to be actually this n gamma, this graph, the roof that I've shown you. And then the idea is very nice, because the Morse discriminant is some hypersurface given by some polynomial, right? F of a, fa. I don't care much about what kind of polynomial it is, but it's a polynomial in cardinality of a variables, because the variables are the coefficients of a general polynomial with support a. Then if instead of those variables, instead of those coefficients, I plug in these functions of t that were in my family, then I would obtain a polynomial in one variable. And it's not very hard to see that the degree of this polynomial is going to be the value of the sought support function on this covector. So here the story is, again, as input we take a covector, as output we take some family of polynomials, or like a polynomial in two variables. We added one extra variable, such that the Newton polytope of it is this polytope and gamma that we have seen a couple slides before. And then basically, if I can, for this family of polynomials with generic coefficients q and v, which are complex, find the number of values of the variable t such that the polynomial ft gamma of x is non-Morse, then I won, because that's going to be literally this number of these points, the number of these values t is going to be the value of the support function at the covector gamma. So we have reduced our problem to the problem for how many complex values is the polynomial ft gamma non-Morse. So then, in order to describe the Newton polytope, we would, for basically all sorts of covectors with non-negative integer coefficients, coordinates, solve this algebra geometric problem, find this number of parameters such that the polynomial, the corresponding polynomial is not going to be Morse, and that will give us the answer. And that's how it works. Now the question would be how to find this number. And here we come to like the hardest part of the talk. So I will still try to be somewhat clear. But here is the idea that if we have added one more variable, then why not to add one more variable? So we added the variable t, but we can also add one new variable y. And here how it goes. So I can consider now in C3, like in three-dimensional space, I can consider the hypersurface, somewhat a tautological one, that would be given by an equation ftx minus y equal to 0. So you probably have noticed that I have dropped the notation gamma from everywhere in this picture, because I said we are solving this problem for every gamma. So, and now I will show you how to do it for some particular gamma that we have taken. So therefore I drop the notation gamma, but of course everything depends on some gamma that is fixed. So we consider this this tautological kind of hypersurface that would contain basically the points tx and the values of the polynomial ftx. So they will be living in this variable y. That's the point of it. And then what I can do, I can consider the projection that would forget the coordinate x. So xyt will be sent to yt. So I project this hypersurface onto two-dimensional plane, forgetting the coordinate x. And then I should consider the critical points of this projection, and these are going to be given by polynomials. So this defining polynomial of h and the partial derivative with respect to x. So this is going to give us this blue curve that is just the singular points of this projection. And then the projection of this curve will have, so will be just this curve D drawn here somehow. So, and this curve will have nodes and cusps. And nothing worse than that, because of this condition that we enforced on the set A. So, and then the idea of the solving this problem is that for such a curve C and its projection D, I have to compute the number of nodes and cusps of this curve D, and the number of cusps is going to be the support function of the caustic, and the number of nodes is going to be the support function of the Maxwell stratum. And then if I compute the support function of the polynomial that was Maxwell stratum squared times caustic, then the thought support function would be 2 times nodes plus cusps. But if I wanted, for example, to compute the Newton polytope or support function of the polytope, Newton polytope of the Maxwell stratum, then I would just have to take the number of nodes of this curve D. So this is the moment where the method can be tailored to whatever your needs are. Okay, and now for the last, I don't know, 5 somewhat minutes, I will explain how one deals with finding the nodes and cusps of this curve D. Here is a little reminder about the polytopes we are working with. So we have a fixed covector, and then with this covector we associate this graph, this polytope n gamma, which is the Newton polytope of the polynomial ft gamma of x, of this Vero or Khovansky polynomial. And this is the Newton polytope of the polynomial defining this hypersurface H that I told you about. So we have 3 variables here. So this polytope is 3-dimensional. And it looks very simple because it's a pyramid with like extra point corresponding to this monomial. But the base of this pyramid is actually this polygon. So, for example, if you want to compute the volume, the lattice volume of this polytope, it's going to be just the area of this polygon. And we will need it on the next slide. So the idea how to find this number of nodes and cusps is that one can use, one can do it using 3 equations on the nodes and cusps. So the first 2 equations are very easy and they fit into one slide. First of them says that we actually know what the number of cusps is. Because we know the result of Gelfand, Kapranov, Zelevinsky, we know the support function of the classical discriminant. It's a classical result, and it's whatever. It's I think I even slightly messed up with these coefficients, but it doesn't matter. It's approximately the same as area of this polygon, minus some terms that actually only shift the polytope in the end and not do anything with it. There is one more equation that connects the early characteristic, additive early characteristic of the smooth locus of the curve D and the number of nodes and the number of cusps. And it follows from Bernstein-Kushnirenko-Khovansky theorem and the additivity of early characteristic, and it looks also not so bad. And then the problem with these 2 equations is that they are not enough. They don't suffice. They don't help us to find the number of nodes. You can't deduce it. We need one more equation. And here is a little scheme of how to get it. So we have a curve D with some number of nodes and cusps. So actually, we can now perturb it to get a curve Y with the same Newton polygon, but already smooth. And if we do that, then we can compare the early characteristic of this curve Y and the curve D, right? Because we can just take the curve D, then cut out the neighborhoods of nodes and cusps, then glue in the Milnor fibers and count their early characteristics. And we would get that actually the early characteristic of our curve, singular curve, is related with the early characteristic of the smooth curve Y with the given Newton polygon. And so we would get something like, so the smooth locus minus the number of cusps is equal to the area of the Newton polytope of the curve D, which is known. It's involves some notation to compute it, but it can be purely combinatorially computed. But the bad part of this is that, of course, whatever I wrote here is not correct, because I didn't say, and it's actually in general not true, that the curve D is Newton not degenerate with respect to its Newton polygon. And therefore, the problem is that there might be some singularities at infinity. There might be some bad points on this one-dimensional orbits of the toric surface associated with the Newton polygon of the curve D. And if we don't know their contribution to the early characteristic, then we can't solve our problem. But the good thing is that we actually know it, because this was done. It's like my work, my previous work before I started this project. And actually, the idea here is that, well, we have to take these points into account to compute their contribution to the early characteristic, and it can be done purely combinatorially, again, using the set A. Let me, I don't know, it feels like I'm not having much time, so unfortunately I think I should skip, or I don't know how much time I can still get, Johannes?
I think, I mean, why don't you take your time? I mean, we started 5 minutes late.
Okay, then, So, of course, I'm not going to tell in details what kind of singularities we will have at infinity, but let me at least show you an example, somewhat general example of when precisely this singularity with like can happen. So let's for a second forget about the problem that we were solving, and let's try to look at the following problem. So suppose we have a curve C, which is a one-dimensional complete intersection in three-dimensional torus given by a pair of polynomials with given support. And suppose this support we also fixed as this is this set drawn in the picture below. And now let's so in this picture, what is comfortable is that there is this so locally near the orbit of the corresponding toric variety associated with this polytope. So locally the picture looks like this. So we have like kind of this vertical plane like this, and this is the, like, say, one-dimensional orbit on which we have like a bed curve of whatever. Sorry, yeah. So I should be more precise. So again, I consider a curve, complete intersection curve given by a pair of polynomials with this support. So it's drawn here, like locally near this, the corresponding orbit of the toric variety. So this locally it will be like four branches that would intersect this orbit transversally at 4 points, and the projections of 4 points will actually end up in 1 point here, red one. And therefore, the corresponding branches will somehow intersect the this axis, this green axis. And in order to understand what kind of singularity we have there, we need to see how these branches intersect each other. So how they touch? Like what is the contact order of contact between the branches? And apparently, what follows from the work that I've done, that one can see this information combinatorially looking at the set A. And here is exactly how. So what I can do, I can take my polytope, I can take this corresponding face gamma, and take the points of the support set, which are marked red, that got to this face gamma, and those are 0, 0, 1, 0, 0, 0, 4, 0, 0. Now I can forget the last two coordinates of these points, and I get the set 0, 4, right? Then I can move this face further, just like one step further into to the direction of the polytope, and see if I get any points of the support set. And I get a point 2, 1, 0. And I forget the last two coordinates of again of this point. I get 2, and in general for now I have the set 0, 2, 4. And then I do once more, and I say next step I meet the point 1, 2, 0, and I forget the last two coordinates, and I get the coordinate 1. So now I've got the set 0, 1, 2, 4, and I can continue this process, and I will get a sequence 4, 2, 1, and so on and so on. Actually, using this sequence, I can deduce that the corresponding singularity that we were wondering about would be 4 branches divided into 2 families, such that if you take 2 branches from different families, they intersect transversally. And if you take branches from the same family, then they intersect, just like they touch with order of contact 2. So I could somehow read it from the sequence for each of the like associated with this phase of the Newton polytope. And I can do it for every other phase to actually like restore what's happening on each one-dimensional orbits of this toric variety associated with the projection curve. And all this information I get purely from the set A. And the nice fact is that the early characteristic of the corresponding singularity, if I know the sequence, can be just written in terms of this sequence. And this sum, it's written as if it's infinite, but actually it's finite, because if my set generates the lattice in the vertical direction, and I like always assume it, and in our case it's also true because I say that this set A we start with should generate the lattice, then actually this sequence will stabilize at 1. And the sequence of, okay, yeah, I probably, so yeah, so as I said, there were sequences 0, 4, then 0, 2, 4, 0, 1, 2, 4. I have to take the indices. I'm sorry, I forgot to say this. I have to take their indices of the sublattices that they generate in Z. And the index here will be, if 0, 4, it's going to be 4. For this part, it's going to be 0, 2, 4, so the index is 2. And then 0, 1, 2, 4, the index is 1, and so on. And if my set in this vertical direction generates the whole lattice, then this sequence will stabilize at 1, and this sum will be finite, and it will give me the earlier characteristics of this singularities at infinity. In general, they are called forking path singularities, and they were introduced by Alexander Asterov, I think, and in some different work, and somehow they appeared in the work that I've been doing as well, which was very nice. So final words on how it's applied to our situation. So we solve the same problem. We are trying to find the number of nodes and cusps of the projection curve for the complete intersection given by polynomials with support A tilde gamma. So with all those points in this pyramid, and then the Newton polytope of this curve with when we project the Newton polytope of the projection curve will be so the Minkowski integral, whatever that means, which can be combinatorially computed in terms of the set A, and it's not the issue, but at the one-dimensional orbits of the toric variety associated with this polytope, there would be some singularities at infinity, and to determine the types of their singularities, one has to do this procedure of shifting the facets and seeing like in which sequence, in which order we get the points of the support set. When we do this, just for every of these facets, and we will get this information. And that is basically how we end up realizing that the combinatorial data we need would be the subdivision. So like basically the monomials that dominate, the significant monomials of the tropical polynomial, the order of the critical values, or the order in which the continuations of those intervals in the graph intersect the vertical axis, which would determine the shape of this polygon. Sorry, and finally, why we needed those sequences, so orders in which the other non-maximal monomials intersected the vertical legs of the tropical polynomial, is basically because we needed the sequences for each of the edge of the tropical of the polytope delta. So we needed to shift them and actually get the sequence I that would determine the forking path singularities at infinity. And basically, this is how I got the data. And this is how I understood which data I need and which polynomials should be considered Morse, tropical polynomials, which should be considered Morse. Those are the polynomials such that this data can be readable. And this is how I got those conditions. And to finalize, we were able to find the number of nodes of this projection curve D using the system of 3 equations. And the third equation you can treat somewhat like a black box, but all of the summands we know purely combinatorially how to solve. And looking at the left-hand side, you see why actually taking a square, so Maxwell stratum squared was more practical, because it's very easy to actually extract 2 times the number of nodes from the system and not divide anything by 2. But if you want, you can divide, and there is no problem with it. And the final thing I want to say is that if in this dual language, the vertices of the Newton polytope, say in the case of A is equal to 1, 2, 3, 4, would be like different shapes of like those roofs, and where you actually have to take into account also these insignificant monomials, say in this case, because they are different only as you see here. So like the shapes are the same, the subdivisions and everything is the same, is that if we take this edge and start moving it down, then we first meet this point and then this point. While in this case, when we move the same edge down, we first meet this point and then this point. And that's actually gives us 2 different vertices of the Newton polytope, for example. So this is the moment where you can see that actually those insignificant monomials, they do matter. So this is everything I wanted to say. I'm very sorry for the delay. All the details you can find in my preprint. I will be very happy if you are interested enough to look into it, and you are very welcome to ask questions if you want, but thank you very much.